Welcome to lesson 4. In the first 3 lessons, I've been showing you how you can prepare well structured root programs which will help you to analyze your data from the neutron detector array NAND at IUAC, New Delhi. Now here I am going to try and give you a more realistic example so that what we have seen so far is fine. In fact, that's the complete program. You won't really need much more than that. But let's run one example here today so that you get used to how you can make a little bit of changes in the programs to suit your data. So, if you don't change your programs at all, if you just try to run the programs blindly, it's not a good idea. You might just see blank spectra, things won't work. So, you must go through all the programs which are available here in my website, and then you must make small changes which will help you to get the programs running for your data. In fact, I would urge you to also write your own programs yourself. You can use the programs I have written as a kind of a guide. It's very important that you become well versed in writing root programs so that you can try to write these kind of programs on your own. And some little bit of programming and debugging is always required when you are working with your own data. A big problem in all these analysis for neutron detector multiplicities is that when you acquire the data, even for the same beam energy and for the same target projectile system, there are occasions when the beam is lost and the run is stopped and a new run has to be started. But in case the beam is retuned, the bunched beam is retuned, in that case there is likely to be a time shift. So the reference time, this changes after the beam has been retuned, and all your time, that is your TDC spectra for all the neutron detectors, they would be slightly shifted compared to the previous run. So if you are just placing all your files, run files in a chain, then you might experience difficulties with this time alignment issue. How do you sort that out and how you can correct that? This is I will be discussing in the next video. But in today's video, I will be trying to guide you how to make the small changes which you will need depending upon your particular experiment. So I'm going to take on a new set of data. The new set of data which I am going to work with here, I am not really giving you access to that data because the required file is actually big. So we won't have that data file, but you will be able to see how the changes are made and the changed programs, the modified programs. When I make modifications, I will archive them for you in NAND04.tgz, which you can download from my website, and then you can go through these programs. Also, you already have more or less the same programs already from the previous lessons, lesson number 2 and 3, where these programs were first written, and here there are small changes. So you can go through these small changes also if you were to download NAND04.tgz and then unpack it. So this is the website where you can get this file, get hold of this file. And when you get hold of this and then when you unpack it, you will see these programs 1, 2. There is a new program 2A which I will introduce here for convenience, and all the 7 programs are changed a little bit. You will see what those changes are. Now for today's lesson, I am going to read the name of the file. The name of the data file is here, mysampledata.root. This file is big. It's 442.6 megabytes, and so I'm not giving you this file on the website. And when this file is run, it will actually run when you loop through the events, it will run for a longer time, much longer time. The previous one, it was completing instantly. That won't be the case when you have real data. So that's why I am running this example for you. Now, this sample data file is actually taken from data which has been collected using the LAMP system and not ROSNIAS. So the older system, LAMP system, used to take the data in ZLS and then you could convert it into root file. And when that conversion is done, the name of the tree, in this case, it is called as LAMP's tree. It could be something different, anything it could be, depending upon how you did the conversion from ZLS to root. And then you would have named the tree at that stage. So in all our programs, we have to take care that the tree is named correctly. And the other thing is that when this conversion was done, the parameters were saved not as double, which ROSNIAS, ROSNIAS keeps all the parameters acquired in double, but that's not the case with this data. This data is has saved the leaves in int. So first we should see that what way the data was saved. So let's look at the file itself, mysampledata.root, and then just check it out. That should be always your first step. So you run root from the command line, and then you open this file. When you open this file, all of you know the command. That is command something like tf is equal to new, and then you say t file, and then you give the name of the file. Again, today I am dealing only with one file, whereas in your case you would have a chain of files, but then you can take any one of them and do this kind of diagnosis on it. So here I have opened the file. Now when you open this file and you do a .ls command on it, then you see that this is what the tree name is. The tree name is called LAMP's tree. You are always dealing with the current cycle. In this case it is LAMP's tree 16, and LAMP's tree 15 is a backup to that. So when you don't mention the cycle number explicitly in your work, then it always picks up the last cycle. Okay, so first let's investigate the parameters. That's done with the .ls command. So when you do the .ls command, then it will list for you the parameters. And so this sorry, not the list command, but the list command ls was to get the name of the tree. Now that you know the name of the tree, you take the tree. So that's LAMP's tree, and then you ask for the names of the parameters by using the print method. And when you do that, you see all the parameters in it. So don't worry right now about the parameter names themselves. I'm going to show you the parameter names soon, but note that they are all of type integer. So this /i, this indicates the type, and in this case it is not double, but it is integer. So that's why you have to make changes in the programs. All the programs which we will run now, you will have to make these changes. This is the very basic change. Everywhere the tree name is to be changed to LAMP in all the programs, and also in all the programs you have to define the leaves as int in and not as double. So this is one change which we will make in all the programs. The other thing is to take note of how many detectors are in use. So here in this sample data, I have 50 neutron detectors. So this is another change which you will have to make in the programs which are using neutron detectors, to define the NDET number of detectors as not as 50 but as 49, because again this is a typical situation in many experiments. Although 50 detectors were defined in the setup, but one of them was not in use. So actually there are 49 detectors. So NDET will be set to 49 for today's lessons programs. Okay, so that's one. The other thing is that in almost in all the real experiments, the TDC calibration should be done. You should not take the calibration of the TDC based upon the range setting of the TDC. You should be using a TAC calibrator, and so when you do that, then you will come to know the slope and the intercept of the calibration for all the neutron detectors. This now out of them, the calibration intercept is not important. What is important is the slope. We need only the slope because we are going to deal with time differences and not with absolute time. So we don't need to record in a file the values of the intercept, but still what we need are the calibration slopes. So you will have to prepare a file. You can see that file here. So it is called as tcal. This is the name which I have chosen, tcal.txt. This text file, you will have to prepare this for your data, where in the first column I have listed the parameter name, that is the time of flight parameter corresponding to detectors. So TOF 8009, for example, had a calibration slope of 0.0857619. The second neutron detector was 8027, and that had a different slope. And so all the slope values are to be written into this file, where I have made two columns. I will show you how and why we have made the first column also, which is strictly speaking not necessary, but I just do it so that, you know, in experiment where there are many detectors, one tends to get confused. Sometimes you might put the wrong values of calibration by mistake. So to take care of that issue, I have kept for all the 49 detectors the name of the time of flight parameter in the first column, and then I have put the slope of that in the second column. Right. So that's one thing, the calibration of the TDCs, and they are now different for each detector. The other thing which you have to see is what was the size of your multi-wire proportional counter. Now in the previous experiment which the sample data which I presented, the size was different. So here the programs will require modification, because here now the data which I am dealing with today in this lesson, the multi-wire proportional counter was 11 centimeters in the horizontal direction, and it was actually longer in the vertical. So usually we place the multi-wire proportional counter so that, you know, it's a rectangle and you have the bigger dimension horizontally and the smaller dimension in as the height. But here the multi-wire proportional counter is actually in height more than the width. The width is 11 centimeters and the height is 16 centimeters. So when you make the constructors for the histogram in all the programs, whenever you are writing this histograms, when you're making histograms connected with the multi-wire proportional counter, the range after calibration will have to be set appropriately to cover this region of 11 to 16, and with a little extra on both the sides. So we'll see that now. By the way, the calibration of the multi-wire proportional counter, I explained to you already that it is done using a mask, but this generally speaking is done in the detector lab, and it would be done already before the experiment starts. So the calibration values are available during the experiment, and in fact they are made available before the experiment starts. We used to also do this calibration online, that means with beam or even without beam, but using a source, but inside the scattering chamber of NAND. But that is not necessary. This can be done in the detector lab. So nowadays most of the time the calibration of the MWPC would be done before the experiment starts, and it will be done in the detector lab. So the values of the calibration would be available to you from that. Right. So let's see. First thing is, you know that you must start with the program 001. In program 001, there is no change except to change the name of your data file and the name of the tree. This is the only change, and then you can run it. So if you look at prog 001, I show it to you on the screen. It is exactly the same as what I presented in lesson 2, except that my file name has changed and this is the new file name, and the tree name has changed and this is the new tree name. And then we run it, and it basically this program gets the list of leaves, and then it saves that into a file. The name of the file where it is saved is called paralist.txt. So you are going to see that now. So when you run this program 001, so here I am going to compile it and then I am going to run it. So program 001 can be compiled using the compilation command, which is available in the first line of the program. We paste it here as usual and then we compile it, and after the compilation has been completed, then we will now run it ./prog 001. This does the job, and now you see a new file got created, and that is paralist.txt, and this file is going to look like this. So this file has got two columns. First is number, which is just 1 2 3 4 5. As you know, I didn't want to start with 0, so I started with 1, and then it lists. Now here you see that the order of the parameters is different than what we had when we prepared this file for the previous data set, which we considered in lesson 2. And there are also other parameters. For example, the E parameter, which we don't use generally. This is the third signal from the photomultiplier tubes connected to all the neutron detectors. We don't require that, but it's collected and it's here. And so the numbering goes completely different. And the MWPCs, they come in this data, they are coming at the end. So this is your no, they don't come at the end, they come somewhere in between. Yeah, it's here. So these are the MWPC parameters. And then again the PSD and time of flight continues. There are even some empties. There are some parameters being not used. These are two monitors which are there. So the first thing which we are going to learn how to do is we are going to make changes to paralist.txt and keep the same parameter ordering which we had when we prepared our programs. Because if you do not do that, then all the programs will need to be changed so that the numbering of the parameters points to the correct parameter name. So this would be a little bit more difficult to do because the parameters are slightly scattered in terms of the order in which they appeared in my paralist.txt. So rather than struggle with those changes, and those changes will have to be made in all the 7 programs, it would be easier if we corrected paralist.txt itself, because the order of parameters in a root file is unimportant during analysis. So what we are going to do is that we are going to edit this file paralist.txt, and for that what you can do is that you take paralist.txt and then you make a copy of it so that we don't lose it by mistake. And so the original one you save it, but then you take this and then you edit it and do the needful in terms of reordering and removing of unnecessary of the unused. Not, I wouldn't say unnecessary, you might need them later on, but right now we are going to remove the unused parameters from this file, not from the data itself. The data, we will never make changes to the data itself. The data will remain in the original condition. What we are doing is in the listing we are going to make changes. So since detector 8135 was missing in this data, but it is there in the list. So if you look at the paralist itself, you will see that 8135 is there. It is here, but at the same time there is no data in it. So because this detector was not used. So what we are going to do is we are going to eliminate that one. We'll keep only the 49 detectors which work, and we'll remove the E's also because we don't use it, and we'll shift the parameters connected with the multiwire proportional counter 1 and 2 we'll shift it towards the beginning of this file. And also notice that there is a slight change in the names. For example, we considered this one to be called as MWPC1 underscore T, that is the timing parameter, but here it's called with the word anode. So don't change the names. These names are important because these names are inside the root file. If we change it, we won't get access to these parameters. So do not change the names of the parameters, but place them the order and remove the unwanted lines. Keep on. So finally our lines, you see here, there are so many things which we are not going to worry about. These empties and these x sum and y sum differences, we are not going to make use of these parameters, so we don't want them in the file. So what will the new file look like? So I have done that for you. I'll just to save time in this presentation, I'm going to just copy it for you, which I have saved earlier, so that I show you that now. I have it here, and I shift it over to the place where I am working. So here it is. So I paste it here, and this is my paralist after editing. This should be having the proper name. In order to work properly, I will give it the correct name, which is paralist.txt. And for safety, I have a copy in my so-called extra, which I have made another directory here. So for now I have shifted it from there to here. So this is what I want you to construct when you have your data. So in the beginning, so this conforms with the way the programs were written. That's why I am rechanging. So the first 10 parameters, they deal with the two MWPCs, and from the 11th onwards we have alternately PSD and TOF alternately, and nothing else. The other ones which we don't need, they are removed from this listing, and we end up here. The reason why we have 108 of them is because there are 45 detectors, each with TOF and PSD. That comes to 90 parameters with 45 detectors, and then you have these ones which are the MWPC parameters. So MWPC parameters, and then TOF and PSD alternately. That's the thing, without any change in these names. So, and also the order, if the order is different, I meant here I don't make any change in the order. So here 8009 will be my first neutron detector, 8027 will be my second neutron detector. So this will become important later on when you are actually figuring out the angles. So when working on the detector angles, which we shall do in a future lesson when we do the moving source fit, at that stage it will be very important to know the angles. So in order to not lose that information, we preserve this file so that after the analysis and the extraction of the neutron spectra is completed, we will know the angles also of the detectors based upon these labels. So these labels are important. Okay, so that was how you correct the paralist.txt, and after having made these changes, what other changes we'll need, I am going to run through that. So basically you will have to write and that is equal to 49 in all the programs wherever ndet is used, and the adjustment of the indexes of the parameters p will be not much, because we have reordered the file paralist.txt itself. So it now matches with the way the programs have been written. The only thing is that in this data it was MWPC1 which was at the forward angle, not MWPC2 as in the previous data. So the program which I have presented so far, all of the programs, they assume that it was MWPC2 which is at forward angle. So this is the one change which we have to make in the p indexing. Except for that, there won't be any p indexing changes. Now you know that we would like to run prog 2, and then we would like to save the cut, and that cut we will still call the same, cut t. We won't change the name of the cut, because otherwise the programs, subsequent programs will need changes which we don't want. So we stick to almost all the conventions we have used so far, but we make only the following changes. So for example, in program 2 you will have to only make the change which we declare the leaves as int instead of double. This is the main change. And you will also have to change the name of the tree as lamb's tree, because that is what it is. And the other thing which I am doing in all the programs, I am going to introduce, I'll show you what it is inside. I am going to introduce a status print inside the loop, because this file being longer, having more entries, it runs for substantial time. You will see that it runs for about 90 seconds. So during that time, if the program is quiet, then the user gets the impression that he's not sure what's happening and the program may not be running. So what we do is we also print out the progress as we run through the entries loop. You may be also interested to know how much time the program took. You must keep a watch on it, because in case you rearrange these programs, or you write them again on your own, always use a timer and make sure that your program is running as fast as possible. So to know how fast your program is running, you compare it with what I got, which I show you now. So if your computer is not slow, you should be able to get these programs running. My execution time, which I show you now using this timer, that's going to be quite small. 90 seconds is the time it took for this file which I have. And then we do it, then we draw the cut, and then we save it. We save the cut inside work.root. So this is how work.root will get created. So this one I will demo for you. We now have to kill the previous program which we are not interested anymore, and now we are going to run prog002. My prog002 is here, and the only changes I made in it compared to what I presented before is that I have put the name of the tree here corresponding to this situation, and then I named my leaves as I declared my leaves as integer instead of double. Here you see the timer in use. So this is my timer part. It has got two quantities, start and end, and when my loop over event starts, then I start the clock, I call it as start, and when I finish the loop at that stage, I call the clock reading as end, and then the number of seconds which have elapsed can be calculated from the difference of the end and the start, and then I print that out. So this is good to keep this logic in all your programs always, because the loop running is slow, and you can watch out for seeing that the program is running fast if you time it. And so let's now go through this run. In the file list.txt, by the way, you should put the names of the files which you are now dealing with. So my file, I'm dealing with only one file, and that is going to be my sample data.root. Here you should put all the files which are the same beam energy and the same system, target projectile system, in order to form a chain of those files. So let's run program 2, and when program 2 runs, it will create a new file. When you try to, it won't create this work.root till you draw the cut, and then you try to save the cut. At that stage, the work.root will be created. So I just demo that for you. So what we do is, first we of course need to compile. No, so this one we don't want to compile. We want to run it from the command line, so that we can see the spectra on the screen, and then we can draw the uh, tcut. So this one need not be compiled, so I'm going to run it directly. So you say root, and then either you can from here itself you can put the name of the, instead of putting a .x and then running, you can also do it this way. So if I run this command, it will run root, but this macro will get loaded and it will run directly. So I do that here. I will just show you how this program is running more clearly without distractions. So let's run it now here. So now you see it's processing this macro. It means it's loading now the entries. The number of entries which I had was about 10 power 7, and now the processing has started, and this line is very important which I have put where it shows the progress. I'll show you this line in the code while this program is running. I can show you that. So in program 2 I have the status line now. Apart from this timer, I also have inserted this status line. So this status line is shown over here. So what it does is that it uses the /r rather than /n. So the /r takes the carriage return to the beginning of the line without scrolling to the next line. If you put /n, then you will get the screen also giving the status on a new line, that is line by line, which we don't want, because if the screen were to scroll over here, not only the program would be running slow, it would also look much worse than the situation than what I'm doing here. So it's a simple command. And don't print on every event, because then it will be too much. The program will get slowed down. The printing itself also slows the program down. So do an occasional print. So I have done the print after every 5,000 entries. As usual, I use +1 because the timing of starting from not from 0 but from 1 is what I prefer. So I did that here, and this is my status print. Insert this line in all your loops so as to watch the progress. So while we were talking, this program completed. So you see that now I am also printing out this. So this is the time it took, 94 seconds it took, and you can calculate the speed. The speed is 109,000 events per second. In that much time this program completes, and then you have over here the spectra. So this was my multi-wire proportional counter, first one. This is timing. I'm talking about the timing, multi-wire proportional counter T, and this is the timing signal in the second detector, and the two-dimensional spectrum of T1 versus T2 is given here. So here what we have to do is that we have to draw the tcut, which will select correlated events. So this has got the events which are correlated in time, which corresponds to the main region over here. The region should be selected, and we discard the events which are far away, which have lost the time correlation because they are arising from random coincidences between the elastic scattering and the fissions. For example, so you have elastic scattering, you have scattered beam, you have the random coincidences. Okay, so and then I'm not repeating for you the procedure used to save it inside the file work.root. This you can see from the previous lesson how it's done. When you do that, so the aim was to draw the tcut and to save it. So that's explained with these lines. It can be done. But now I want to tell you one important point is that when you draw the tcut, be a bit generous in the size of the tcut to select the correlated events, because if you do not, you will be losing statistics. So your tendency is as a student to think that okay, so this must be only this dark yellow region. Some people even choose a very small region in this, thinking that they are making the right selection. But no, you should be selecting all the events which are correctly time correlated. That means which are not coming from randoms. And for that, it is good to make a selection like I have shown on the left side, which I have labeled as correct. If you make a smaller one, there isn't really any problem with that. You can choose a smaller one, but then you will be losing statistics. So we don't want to lose statistics. We have collected this data, so whatever data is valid, we should try to include as much of the valid data as possible without leaving out the statistics. Okay, so you can do that, and then you save it, and when you save it, you will get a new file, work.root. I have kept my work.root here. I will shift it over into the place where I need, and the name of the file is work.root. Just for safety, I renamed it here, but basically work.root. So this is where I have now this tcut saved. Alright, now that we have saved the tcut, let's explore the neutron. I have made another program. I call it as program 2A. Previously, we didn't have it. We used to go directly to program 2. But this, I added this program. So when you get it from my website, you will get access to this program. Also, this will print, which will show on the screen all the time of flight spectra. So that is what I'm going to run now, and so here the changes are not changes, but differences between what you would have written. Make sure that the end date you set it as 49, and then you fill them. The fill command, this part is not changed because the indexing of P is not changed. This is the one which you fill. These are the time of flight spectra, 2J plus 11 parameter number from the file. So 2J comes, because we are alternating between time of flight and PSD, and 11, this comes because we have placed 10 parameters corresponding to the multiplier proportional counter in the beginning in the order of the parameter list. Now, in order to avoid, when you try to get these spectra on the screen, then basically it will not be zoomed properly. So it would not be scaled properly. You would see, because on the very zeroth channel, on the first channel, the counts would be large, and then you have to then actually drag your mouse over the x-axis and then zoom them in order to see it. To avoid that, you can as well put an axis range command in your code itself, so that all the spectra are directly displayed. So let's go ahead and have a look at program 2A. So program 2A, which you can get when you unpack your tarzip, which is available on the website, and then you will compile it. And the program is similar to what we have been writing, but now there are 49 detectors. So this is what you need to do, define that here. I'm using a timer, so let's keep this line for the timer part. The name of the tree is changed. It's not Rosnia's, but here it's called Lamb's tree, so make sure you put that. And now the event loop. So this is my event loop, and inside the event loop I am building the spectra for the parameters 2J plus 11. This corresponds to all the time of flight spectra. The loop runs over all the detectors, ended, there are 49 of them, and at the end, when all of these are completed, then not only will I print out how much time the program took, but then I will go for displaying them on canvases. So there will be 49 canvases which I have staggered, and then you can see all 49 spectra. But so here is that command, set axis range. This helps us so that we don't have to zoom all of the spectra. If you do not set the axis range, here I have set the axis range between channel number 10 and 4000. So I avoid the first few channels because there is nothing there anyway, and then I don't need to zoom into these spectra in order to have a look. So you can do it without this line this command also, but then you would have to zoom on the spectrum. Okay, so let's run it. So program 2 has to be compiled and run, and the compilation command is available here, program 2a compile me, and pasting it here. I'm not able to do it from yeah, we are still in root, which we need to quit, and now we will run the compilation command. So this is my compiler, so the compilation is over. Now I run it, prog 02a. So this is going to now run over here. So let's keep the other windows minimized so that we get better chance to see what happens. And here it's running. You have to ignore my error which I told you about last time. It's to do with my root installation. So here it's running, and this is the way that the progress can be seen at the end when it will finish. So I just pause the video for a little. Welcome back. My processing is almost done, which you see here. So it completed, and after the completion of the processing, all my 49 spectra are displayed on the screen, and thanks to my setting the range command, I didn't need to zoom them. I can see all the spectra. So these are my the thing to note is that the neutrons are on the right. Gamma peak is on the left in this time spectrum. So the time axis is reversed compared to what we saw in lessons 2 and 3. So that means when we come to calculation of the neutron time of flight, we'll have to take into account the fact that the axis is reversed. So more about this later. Now about the execution speed. If you run this program, you'll find that if you run it as a compiled program, it runs within about 90 seconds, and the speed at which the events are processed is around 118,000 events per second. If you run it as a macro, it is about slow by a factor of about 2. So this shows you why we prefer to run the programs which are compiled rather than as macros. So compiled programs, they run faster. Coming to program 3, there won't be many changes here. You will have to just make sure that you set the number of detectors correctly, that you rename the tree, that you give the correct name of the tree, and that you change the leaf type to integer instead of double. This is important. This one only is important. The rest we've already seen, adding of the progress status line and the chrono timer. But you need to change the set user range while calculating the position of the gamma peak, because the gamma peak will now be coming at a different channel number compared to what we had earlier. So whereas earlier we had to we could search for the gamma peak in this range from 2000 to 4000. So here it's valid for this spectrum on the right to search in the region of 2000 to 4000. For the highest number of counts in the region from 2000 to 4000, we would be detecting the gamma peak. But now if you do 2000 to 4000, you would miss the gamma peak entirely. So I have decided to try with 300 to 3000. You always leave out the first few channels where that you have higher counts, so that part is not to be included. But with something safe like 300 to 3000, the highest number of counts from 300 to 3000, you don't need to really go all the way up to 3000. All the peaks will be close to 1000 or so. But anyway, you can have it a little more without any problem. So when you run now the program 3 with this essential change, then it will produce gpause.txt. This is the file in which you have the peaks of the gamma rays, the peak corresponding to the gamma ray in the time spectrum. So this file, I'm opening it for you to have a look. Here you will find that you have got the positions 950, 1058. These are the positions where it has detected the peak. You can just roughly check it. So I showed you from this one that yeah, so the peaks, the gamma peaks are close to in this channel number 1000. So that is about the execution speed and how you can adapt this program 3, and when you run it you get the positions. Now coming to compile to get program 4 compiled and run, the aim of program 4. So program 4 was basically one in which we are trying to build and then save all the detectors two-dimensional PSD versus TOF spectra, and they will be saved in work.root. Later on we'll read these back so that we can draw the T-cuts around them for all the detectors. So here there isn't anything really to change. You just change the number of detectors to 49, make sure the tree name is correct, and the leaf type is integer. Insert the chrono and the printf for the progress, and this program will work. When this program works, then it saves everything in work.root, and then from work.root you want to recover, read these spectra one by one, and then place them, draw the T-cuts, the neutron selection T-cuts, you draw them, and so that's done by this command line procedure. You set the name and then you write it out. So this is similar to what we have done earlier. Now there are 45 detectors, so all the 45 end cuts will be cut ends will be written into this file. Now a word about drawing the cuts. Here drawing the cuts is important not to lose neutrons. The correct way will be to draw a cut like this, making sure that all the neutrons are included. Whereas if you draw the cut little tightly, then you will get little lower values of multiplicity when you do the analysis, which would be wrong because many of the neutrons here have been left out, which are near the periphery of the selected region. So basically what happens is that if you look at data which is very clean like it was in the previous one, there the data didn't have many randoms. In that case you have this situation where you can draw a very safe gate like this. But in the present case there are a lot of randoms seen. I've indicated here what are the randoms and and the gamma is of course here. So while drawing this gate, what we have to do is we have to avoid the gamma rays and you have to avoid the randoms, but you have to make sure that you don't lose any neutrons, because if you lose any neutrons you will get lowered values of multiplicity, which would not be correct. Okay, now let's see how we adapt program 5. Program 5 is to be adapted and then you have to run it. The aim of program 5 was to show you the position spectrum, two-dimensional position spectrum in the multi-wire proportional counter. So apart from these changes, which are similar to changes so far in the rest of the programs, you have to insert the correct values of your calibration parameters, which would be varying from experiment to experiment. So you need to put in the correct calibration which corresponds to your detector. Then you need to correct the constructors of the histogram. See, the histograms for the position will depend, the range of it will depend upon the dimensions of the detector. So in this particular data set, the dimension of the MWPC is minus 5.5 to plus 0.5 and minus 8 to plus 8, and then we need a little extra margin around it, so we have to code according to that. And then we need to make only a small change here in these lines, because this is MWPC 1 which we are slicing, and whereas the program previously written was slicing MWPC 2. So this change also you need to make. Apart from that, because the program is written fairly alright, structured, so you don't have any other changes, and you should be able to run this, and when you run it you will get a picture like this. Here, if you look at this picture, you have the detector, size is such that this was longer along the vertical direction, shorter along the x direction. Normally it is not like this, but here this is the situation. And one more thing I have to tell you is that occasionally you have the situation of left-right reversal. This depends upon you to some extent. You can calculate the position either as right minus left or left minus right. Usually we take left minus right, so that the pictures which we show below, they get oriented left right. But this would depend very much on how the signal has been connected in the experiment. So occasionally there is this left right reversal. You would have to take that into account. Not that it matters at this stage. At this stage you could do it either way, but in the end, when you are assigning the angles to these slices, you have to be careful about the position of the slice, absolute terms, so that you don't make a mistake in where this slice is physically located. So be careful on that. Just for variety here, I have written it as right minus left, but in your experiment you might take left minus right, which would be P2 minus P3. So this you can take care. So this is the picture I get when I run this program, and then I'm going to draw, I'm going to consider, rather not draw, but I'm going to consider the area of the detector between -5 and +5 in the x, and -7 to +7 in the y direction, where I am leaving out some of the data which is near the edges of the MWPC. Now then we divide. Again I am going to take 12 slices, and in this case, instead of taking 4 by 3 which we had done earlier, let's try 3 by 4, because this detector is actually higher, it's taller in the y direction. So let's make 4 slices along y and 3 along x, and then when we divide it up, these are my dimensions of the slices, the positions of the slices. You need to put this slice cuts data into your slice data.txt. So slice data.txt would now show 3 by 4, and these would be the positions of the cuts. So having got this done, this is you can now run program number 6 for doing this, for checking the slices. So eventually you are running program 7, which is doing the real work. This is all for checking. So here is position 6, program 6, which does the slicing by putting conditions on the positions of the slices, and it generates spectra, 12 spectra, 12 slices, just to show you what the position cuts look like. Okay, so this is as before with small changes. Now we come to the last one, and that is program 7. Program 7 calculates the neutron energy, and what is different now, there are two things which you have to take care. One, I already mentioned that the neutrons are coming to the right. So we will use P minus G rather than G minus P. P minus G is where P is the channel number corresponding to the neutron, which is going to vary event by event. G is the position of the gamma peak, which is fixed for all the detectors. But now P is larger than G, so it should be P minus G and not G minus P. And also the slopes on the calibration factors, they are going to vary from detector to detector. We won't be considering only just one value for all the detectors. And so that consideration is already created in a file. That file was over here, tcal.txt. So in tcal.txt we have put in the values of the calibration slope as the second quantity, and on the left we keep just for our reference, we have kept the parameter name corresponding time of flight. So this column, the first column, is not being used except as a check. Just we will verify that we are not making a mistake while typing these. This was for that purpose. And then you can use the expression half mv square as before, and I have rearranged it to give you the equation which is shown over here inside the box. So this is what we are coding in prog 7. So in prog 7, the important part of the code which I will like to show you now is related to the conditions which we have put on the slices are here. And yeah, this is the equation corresponding to this boxed equation here, where you see the slope 1.601 10 to the power 4, and then in the denominator the slope multiplied by p minus g. So this is coded over here. So you notice it is p minus g and not g minus p. And this power function is used for squaring this. And these are the slopes. So the slope is going to vary from detector to detector, and these slopes have been read in. So in this one, there is additionally this function inserted. This one get tcalib. What it does is that it reads these slope values for all the detectors, which is in the second column. The first column is used only as a check. So here I am reading the par name from the first column, and then I do the string compare. So I compare it with what I expect, and if there is some mistake, then I just print it out, and then I exit the program completely. So this is just to ensure that we don't make a mistake, and we put in the correct calibration for each of the detectors. So that's the purpose here. There are 49 detectors. These are the calibration of the MWPC for this experiment, the slope and the offset for the MWPC calibration. And okay, so these are the changes which we have made in it. Rest most of the program is the same. This is the changed tree name. The tree name must be set correctly, and then these are the calculation of the x and y positions inside the multi-wire proportional counter. Then we are looping here over the detectors, and that's about it. And then there is this one which gives the status printing line as soon as we have 5,000 events, and then 10,000 events, and like that. So every 5,000 events we indicate the status. And then finally we save all the neutron spectra in a ASCII file for which we will utilize for doing the moving source fetch. But for now, just to see that we are okay, just one sample spectrum you can draw on the screen on a canvas. So I have chosen this one, which is the first second detector, because the indexing starts from 0. So second detector and second slice, just something at random. There are 12 slices. So the second index you can have any number from 0 to 11, and here there are 49 detectors, so you can have all the values from 0 to 49. So you should actually display all of them, but it should be okay to display some of them at randomly and make sure everything is okay, because we are really going to save all of them but we are going to save it as an ASCII file, and we need not plot all of them. There are in fact too many to plot. So we just go ahead, and then when we run this program, that will finish the job for you. So let's run that now. So the last program, this is the one which I have listed the changes for you which you need to make. So when you're adapting this program, this is a kind of reminder to you for each of the programs, what are the changes typically that you need. So you need to make changes of this type. Make sure that you don't make any mistakes, and when you run, you will get all the 49 detector spectra corresponding to all the 12 slices. So the number of spectra generated here will be 49 times 12. So that is your program 7, and the way of running it you already know. You have to compile it like this, and then so here we will compile it. Let me open the terminal from the correct place. So open in terminal, and then paste the compilation command, and so okay, so here I have done the compilation. Let me minimize this so that it's easy to spot. Yeah, so this was the compilation, and now we run it. /proc007. This will, when I run it, it will run, and when it's finished, then you will see only one sample spectrum on the screen, and all the other spectra, all the spectra, including the one displayed, of course, all the spectra will be saved in ASCII file. So here you see now I have started the program. You need to ignore my error, which is due to my installation problem. But anyhow, the program is running. See, now you can see here how the display is going. So when this program finishes, it displays for you one sample spectrum, and the remaining files, the remaining spectra have been saved in the file. So that file which got created now is in neutron spectra.txt. So this is my final result, and this file, the structure of this file is known to you from what we did in the previous lesson. So basically it goes slice by slice, and within each slice there are in this case 49 neutron spectra. This is my neutron spectrum number 1 over here, and then the second spectrum, and so on for all the 49 spectra corresponding to the first slice, then second slice, then 49 spectra, then next, and so on. So this is the data which eventually we are going to analyze. In a subsequent lesson we will see how the moving source fits are to be done. So that's it for now. This the idea of this short video was to help you to see what changes you need to make in the programs when you adapt it for your data. So these small changes, you must do them carefully. You must make sure that you don't make any mistake, and then only you will be able to analyze your data correctly. And the last thing which is not covered is what to do when there is a change in the time position. So when the beam is tuned between, so when one run is stopped, and even if you are having the same target projectile system and the same beam and energy, it may be that there is a jump in the time spectrum because of the tuning of the pulsed beam. So in that case, what do you do? How do you, if you are putting all the files in a chain, you would experience problems with the shift. So this I will cover in the next lesson, how you can take care of this conveniently. So thank you very much for watching, and look forward to the next video. Thank you.